All right, here's the video guide for lesson 10.3.1. I said in my announcement yesterday that we have moved past our kind of probability, conditional probability. We'll still see it a little bit here today, but this is going to be a different idea. We're going to look at this fundamental principle of counting. What does that mean? And we're going to really look at that with this idea of decision charts, and we'll read the intro to this lesson to kind of get a better understanding of really what we're doing here today. I modified this, so it's not exactly right. We're doing 10.108 to 10.111, I believe, here today. All right. So here's just kind of the way that they're going to open up the idea of the fundamental principle of counting, and I think it's worth reading. And so it says phone numbers in the U.S. are composed of 3-digit area codes followed by 7 digits. License plates in some states are made up of 3 letters followed by 3-digit numbers. Postal zip codes are made up of 5 digits and another 4 digits added. To win the lottery in one state, you need to select correct 5 numbers, all the possible choices of 5 numbers out of 56. And so it leads to this idea of like how many different combinations can we get, and that's what I think is interesting. And I think that's prefaced really well. Like you always see these license plates, and you think like, how many actually unique license plates can they make? And that's the idea that we're going to look at today, and that's the idea behind the fundamental principle of counting is how many different combinations of numbers given some kind of space can we make? All right. And so we're going to start here by looking at Nick's problem. And it says Nick came across the following problem. If a 4-digit number is randomly selected from all 4-digit numbers that use the digits 1, 2, 3, 4, 5, 6, 7. So they're saying it's a 4-digit number, and it's made up of these 7 digits, and these digits are allowed to repeat. All right, and then our question really is, what's the probability that they actually select the number 2,763? All right, Nick knew that he had to figure out how many numbers were possible in order to figure out the size of this sample space. And so we're still kind of with probability in this idea of sample space. But again, the question is, we're looking at all the possible 4-digit numbers that are made up of the numbers 1, 2, 3, 4, 5, 6, and 7, and the numbers are allowed to repeat. All right, so the first way Nick saw this was that he was going to try to make a systematic list, but he gave up after the first few. And so he said, what is the difficulty in trying to create a list? And so I'm going to go to this page, and let's just look at, if I was trying to create a list of all the a systematic list of all the numbers, we would have to start with 1, 1, 1, 1, then we'd have to do 1, 1, 1, 2, then 1, 1, 1, 3, and we could keep going and doing that pattern for a very, very long time, and the list is just too long. And so if I'm going to address Nick's question saying, or this question saying, why did Nick give up, or what's the difficulty? It's just too long. Too many possible, I guess too many possible number combinations. I'll say it like that. Or I could say the sample space is too big. I'll say number combos, though. I kind of like that. Okay. Next question is, so what really that shows me is that we, in a lot of these circumstances, with the fundamental principle of counting, we can't do a systematic list because the numbers are just too big. All right. So then Nick says, what if we try to do a tree diagram? What problem do we encounter with the tree? Well, if we make, and it's going to be a similar thing. There's just so many possibilities here. That in the first decision, it could be 1, 2, 3, 4, 5, 6, 7, like 1, 2, 3, 4, 5, 6, 7. And then you'll already see the problem here. Each one of these has a branch off of it of 7, 1, 2, 3, and I can't fit them all in here, but they would all have branches of 7 off of them. And already, even with the space I'm working with, I run out of room, and that would just be branch number 2, and we'd need 4 of those branches. And so the tree diagram is, again, just too big, too many possible number combinations, or actually I could just say too many branches, honestly. Too many branches for the tree diagram. So again, a tree diagram is not the way that we're going to go about doing these kind of problems. So we keep moving on. It said, Nick decided he needed a shortcut strategy for organizing this problem, otherwise he was going to be up all night working on it. He started to ask himself, how many decisions about the digits do I need to make? And with your team, we need to discuss this first question and consider the next one. How many choices do I have for each decision, so each digit? And so the way that I see this problem is that we have 4 decisions to make. All right, we have a decision to make. We have a decision to make for the first digit. We have a decision to make for the second digit. We have a decision for the third, and we have a decision for the fourth. All right, we have 4 decisions being made. Now, that's that first part right here where it says how many decisions about the digits are being made. 4 decisions because we're making a decision for each digit. All right. Now, the next question, how many choices do I have for each decision? Well, in the first choice, we can choose numbers 1 through 7. So there's 7 choices to choose for the first choice, or for the first decision. The second decision, since numbers can be repeated, we have 7 decisions for the second because it could be numbers 1 through 7. For the third, it's 7, same thing. And for the fourth, it's 7, again, because numbers can be repeated. And for each decision, we have a number 1 through 7 we can pick. And so we are left with this idea. And I think this addresses a problem later on, but I'm okay putting it right there. All right, so then we have that. We made 4 decisions. Each decision has 7 choices to make. And then Audrey is going to bring up this question. She was at her house on the same problem, and she was thinking of a tree diagram. And she asked, how many branch points will this tree have, and how many branches at each point? Well, I kind of already talked about this, and it goes along with part C here. I got to use my pen. I kind of talked about it here. We would have 4 branching points, and we would have, and I'll try to maybe put this in red, we would have 7 choices at each branch point, and we would have 4 branch points. And so you would see it branch this time here, it would branch another time here, and it would branch 4 times for the 4 choices, and then 7 branches each time for the 7 choices. So 4 for the decisions, 7 for, and so the way that they say it, so I can say it correctly here, how many branch points will the tree have? It'll have 4 branch points. 4 branch points. I'm sorry, this is in red. I didn't mean to. 4 branch points. And the way that they say it too, so I don't screw that up. And then how many branches at each point? 7, because there's always 7 choices. So 4 branch points, 7 branches. The way that they say it, sorry. 7 branches at each point. Each point. Okay. And I think in this next one, I've already kind of done it because I already have this chart, but we get to introduce this vocab here. It says, at the same moment, they text message each other and realized they were stuck. When they talked about it, they realized they were on the same track. The problem asked for a 4-digit number, so there are 4 decisions. Simultaneously, they said that we need a decision chart, and the decision chart here is kind of what I already made on that page, and they wrote it on their paper just like I wrote it on mine. And then it says how many choices are there for each decisions, and then how many 4-digit numbers are there. So we already talked about how this is what we have right here. We have 4 choices, 7 digits for each choice, and so we have 7 choices for each decision. But then we have to take it a step further this time and say, how many 4-digit combinations can we make then? How many 4-digit numbers are there if this is what our decision chart looks like? And the nice thing about a decision chart, and I might be able to copy and paste this and put it for D, but the nice thing about the decision chart is we just multiply down the division chart to figure out how many possible choices we have. So if I do 7 times 7 times 7 times 7, I will have my answer for how many possible 4-digit numbers there are when you have this choice of 7. And so for part, I wrote 4 right here, and I think I meant to put D. Okay, D, and then we have E, I believe, right? Yes. All right, and so looking at my decision chart, I'm going to do 7 times 7 times 7 times 7, and that's going to give me my number of decisions here. And so 7 times 7 times 7 times 7 gives me there's 2,401 possible number combinations when you're talking about 4-digit numbers, and each digit can be 1 through 7 without repeating. So that's a really clear example of why we don't want to do a systematic list, and we don't want to do a tree diagram, because our sample space is 2,401, which is a massive sample space, and that's just a 4-digit number with numbers 1 through 7 for each choice. Okay, and then lastly, what is the probability that the randomly selected number would be 2,763? Well, 2,763 is just one of the 2,401 choices, or 2,401 possible number combinations. And so what we say for probability is that 2,000, what is it, the number that they give us here? 2,763. 2,763. That's just one of our choices out of a total of 2,401 choices. So to find probability, we say that we put our one choice. Okay, that was weird. We put our one choice over all of our possible choices. And so we have a 1 in 2,401 chance that that number actually comes up, which gives me a probability of, believe it or not, it's tiny, 0.0004, which as a percentage for fun gives me about 0.04% chance of getting that number. So it's like if you were thinking about like a spy movie, and I know I'll just move on to the next one soon, but if you're thinking about a spy movie and they're trying to crack a 4-digit code that has numbers between 1 and 7, they have a 0.04% chance that they could actually crack that code and get the exact right answer, the one right answer out of the total here. And that is our first example. I'm going to do this decision chart more as we go on, and it'll change a little bit. But again, it's just talking about how many decisions are we going to make, and then how many choices do we have per decision, and then multiplying down that decision chart once we have it laid out. All right, so I'll do this one, and then for 110 and 111, I will do it in a second video. But here we have how many 4-digit numbers could you make with the digits 1, 2, 3, 4, 5, 6, and 7 if you could not use any of the digits more than once in a 4-digit combination. So we can't repeat numbers this time. So like numbers like a number like 1, 1, 1, 1 cannot be. A number like 2, 2, 1, 1 could not be, because we can't repeat numbers. So it changes our decisions a little bit. But we still have 4 decisions to make because we have 4 digits. And so we have a first decision, a second, a third, and a fourth. The first decision we make, there are 7 choices, right? You could choose numbers 1 through 7. So in the first one, there's 7 choices. But on the second choice, there's only 6 choices, because on the first one you chose a number. And so you could say like maybe you chose number 1. And so now there's only 6 choices for that second number. Say on the second number you chose number 2. Can't repeat that. So by the time you get to the third decision, you only have 5. And then after you choose that one for the third decision, you can take away another one, and you would only have 4 by the time you get to your fourth decision. All right. Now, this works like our last decision chart. If we want to find the possible outcomes, the possible sample space, the size of our sample space, we just multiply down our decision chart. So 7 times 6 times 5 times 4, and 7 times 6 times 5 times 4 gives me an answer of 840 possible choices, which you can see is quite a bit less than when we can actually repeat numbers. That's quite a bit less than the 2,401 we saw. And then if we're talking about similarities and differences, I will do that quickly in the second video.